Alright, time for another Shitopedia video. Okay, draftphysics.com, debatephysics.com, video presentation. Electricity. So, winding down the last few subjects here, and it's all really important stuff, and blah, 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 blah. So, but these subjects really deserve extensive conversation, frankly, because there's a lot to it, but I'll give you the really short version. And just as I do in these videos, I try to show the contrast between their theory that doesn't say anything and a much better theory that does explain how the phenomenon happens. Okay, so we probably go over here a little. All right, so the idea is the charge thing. So let's do that real quick. So you really have to kind of understand the function of electrons and protons. Okay, so electrons, well, I should make it is a problem that the electrons really are mislabeled. Okay, they're the really active player and the proton is the inactive player. That is a little bit annoying, but I'm not going to pause for it. Wardrobe failure, or whatever they say. Anyway, so the idea is that there's two kinds of these things in the universe, these pieces of matter, and that they have this property of being charged. And the idea is that there's a complementary force in the universe for the electrons and the protons. So there's two kinds of force, and there's two kinds of matter. And the simple trick is that when a proton force hits a proton, and it's not moving, it will stick, okay, and give it momentum, okay, a much smaller velocity than it's going, but it'll give it momentum in the direction it hits. If it's already going in a direction and a proton force hits, well, then both forces will reflect one of the pushing forces and the force that hits. So it's kind of just a kinematics, whatever comes in comes out again eventually. All right. And then if the electron force hits the proton, it just goes and gets converted into a proton force. So you could understand that all the electron force that hits the proton is turned into proton force, and all of the proton force that hits either reflects or it sticks. So the proton ends up only reflecting red, and the electron ends up doing exactly the inverse and only reflects blue. So proton force hits an electron, it comes out blue. Electron force hits, it pushes or it reflects. So you end up with two objects that basically have these two properties. So it's unlike Maxwell's equations. It's not like this force is going into that force and this force is going into that force. It's that these forces inversely repel. So this force, the red stuff, can't do anything to the electron, can't move it. The blue force can't push the proton, so it's inert. And that means the external force, which still has this red stuff in it, and this side it still has the blue stuff. No red can get from here, no red can get from this side to this proton. No blue can get from over here to this electron. So you can see the pressure differential. That's why they move into each other, is because there's no pressure here and there's lots of pressure still out here. And the reason why they repel is even more obvious. They're producing, the only force they're producing is the electron force at each other. So they're obviously always, all right, if it doesn't stick, it reflects. And so it's going to bounce back and forth here if they're moving towards each other. And if they're moving away from each other, it's obviously sticking, and that means it's making them go faster. So the electron force, all the red force that hits, again, is inert, and the only force that matters is the electron force, blah, 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 pushing the electrons. So that's why they repel. So the protons repel each other, electrons attract each other. All right, and you really have to have some kind of foundation if you're going to do anything understanding electricity. Frankly, you have to understand what charge is. So that's what charge produces, is attraction between like bodies and repulsion against the opposites. So in the atoms, we know that the nucleus is the only place where there's protons. So the argument is the protons are heavier, that is, they're not as easy to move. That's why they got stuck in the nucleus, all right? And the electrons are lighter, and so you have a you have electrons in the nucleus, but you have twice as many protons. And so therefore you balance the equation by having electrons on this outside that are attracted to the positive nucleus, all right, but they're repelled by each other, and so they're stuck in a balance. And the simple argument is, make these a little bigger just for the hell of it. Okay. So what you could understand is if I add, so I have, let's say I have a bunch of these little atoms in something, right? So there's a bunch of these electrons, and they all sense each other in a sense, right? Each electron knows about the other ones. If this one creates more pressure and this one moves this way, then this one's obviously going to feel more pressure and it's going to move, so they balance each other's pressure. So the electron pressure in any substance is balanced. Now if I add charge, okay, so I have some free electrons and I throw them here, and I throw one over here, you can understand that what's going to happen is they're still attracted to that positive nucleus. They can still see it from certain perspectives, right? From certain points of view, they can see this positive charge in the nucleus, and so they're going to be attracted to it, but they're going to add pressure to the electrons. So you can understand that if I add any charge, if I add electrons, dump electrons on this surface, they're essentially going to be like gravity. They're going to be like a weight. And so they're going to push on these electrons. And these electrons are going to push on each other. So the pressure inside the whole substance is going to get higher. So it's like gravity. Okay, so if if I had a surface and I put something on the surface, the thing on the surface is going to put more pressure into the surface. It's going to add pressure. So the total pressure here goes up by any mass I put on the outside. Just increases the pressure. So the more mass, the more pressure. Same thing here. More electrons, the more pressure. Voltage goes up. Okay, so the voltage of the electrons, that is how close they are to each other, increases. So the electrons go from being this far apart to being this far apart, kind of thing. Closer they get to each other, the more pressure there is, the higher the voltage is. And the idea is that you can eject these things faster now because you have so many of them. You have so much pressure. And so what electricity basically is any time you transfer, electrons, you're doing electricity. So any time you have some extra electrons over here in a conductor, and you connect it to some other conductor, and these electrons are really far apart, obviously you're just adding pressure. You're taking the pressure from this side and you're giving it to this other side. And this process of giving electrons usually requires there to be a conductor. You need a vehicle to pressurize. You need a container, where you're going to add the pressure, all right, to hold the pressure. You can't really have pressure if you don't have a container. So that's why a vacuum doesn't transfer electrons. And air or some other medium that has conductive atoms in it can transfer the pressure. So basically when a spark happens, the atmosphere is creating a pathway, of atoms, ions, and now the electrons can jump from atom to atom to atom and get to the other conductor. So it's just a migration of electron pressure. So I guess the key word would be electron pressure. Would be a key concept to understand when you're going to understand electricity. It's just about the pressure of the electrons. The protons are irrelevant. Protons don't move. They don't do anything. They are irrelevant, essentially. I hate to say irrelevant. Of course, they're terribly relevant. But pressure inside the nucleus isn't what you're going to be messing with. You're going to be messing with the external electron pressure. And that's what electricity is messing with something's external electron pressure. So when you add charge, you increase the voltage, you create potential higher pressure. You create something that has pressure that the rest of the environment might have a much lower pressure, and therefore the electrons are going to migrate from the high pressure to the low pressure. So it's just about electron pressure. I guess it's a key concept. All right. So leave us go to their description. Electricity is a set of physical phenomenon associated with the presence of motion, with the presence and motion of matter possessing an electric charge. So they won't tell you what a charge is. It's just some idea that electrons and protons attract and protons repel protons and electrons repel protons, but they're not saying any of that here. All right, so we'll say electric charge is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. Is that telling you how the charge works? No. Okay, electric charge can be positive or negative. So again, in all these cases, there is no negative. Okay, there's just the amount of pressure. So you increase the pressure or you have a low pressure, but you never have zero pressure or unpressure. All right, so that's just misleading. I mean, a negative 5 volts is always negative 5 volts relative to some arbitrary other pressure. It's not unpressure. It's not a true negative pressure. All right, it's just less than the surrounding pressure. All right, electric charge. Electricity is related to magnetism. So that argument is I've made in previous videos, but magnetism is about a dipole. Okay, so when you make dipoles, you create a signal that is polarized, and that polarized signal is magnetism. All right, both being part of the phenomenon of cannot click anything. Okay, electromagnetism as described by Maxwell's equation. So again, Maxwell's equations do not describe anything. They really don't. They define some relationships that exist, but they do not in any way give you any kind of description about how it works. Nothing. So it really is, that's an empty statement. Common phenomena related to electricity. So what is that even? What is this? Common phenomenon. Like lightning, static electricity, electric heating, okay, electric discharges, and many others. Electric heating, so again, this is just about what you're doing to the conductor. It's a poor conductor. It doesn't move the electrons very efficiently, and so the electrons end up, okay, pushing force out of the conductor. It starts falling apart. All right, the presence of either a positive or negative electric charge produces an electric field. So there's no electric field. There's just a magnetic field. So, but there's no electric field. You have a charge on a surface. There's no electric field. There's just the fact that you have a surface that looks like high pressure. There's all blue force coming off of it. A lot of blue force and very little red force. So yeah, it looks a certain way, but that certain way is more magnetic than it is electric. Okay. The motion of electric charges is an electric current. So the current part is just the volume of the amount of pressure. So the current shouldn't be confused as being, let's see how to say it. It has, the amperage is the number of electrons. The voltage is the pressure, how fast they can move. So the speed volume is a very good analogy to voltage and amperage. All right. But the idea of current is about wattage. So it's really just about what's the total pressure being exchanged. So you can understand if you move something with a lot of little things moving with a small differential in pressure, or a very few things with a very high differential in pressure, that's the same thing. So one bullet going very fast, 10 bullets going very slow. Same momentum. So it's more like electric current is the total momentum of your electric event. And the momentum is going to be decided by mass, which would be the volume times velocity, the pressure, the speed. And produces a magnetic field. Okay, well, it obviously does produce a field, and the only thing it's producing, though, is a reflection to the universe. The universe comes in, the force, the red and blue stuff comes in, hits something, and it reflects it based on what colors it has. And so as you put electricity in a wire, what you're doing is changing the way the wire looks because you've got a higher voltage, which means you have more electrons. So they're covering up the proton field more. All right, a magnetic field. In most applications, Coulomb's law determines the force acting on an electric charge. So that's on a frickin' electron in most cases. So all this is about electrons. I mean, it just is. It's about electron pressure. That's electricity. So you ought to just limit the conversation to migrating the pressure of electron pressure in a mechanism, a conductor, or on a surface, or on even an insulator, even a piece of glass. You're just saying how many electrons are in some kind of location, and that'll tell you the pressure. A piece of glass doesn't connect all these electrons. The electrons can't feel each other in a piece of glass. That's why they can't convey the pressure. So when you increase the pressure on one atom of the glass, you don't increase the pressure on the rest of the atoms. The individual atoms have to hold the charge. All right, an increase in charge. Force acting on the charge. Electric potential is the work done. So just nonsense words. The potential doesn't do work. Something active has to do work. So again, it's just silly to say that. So we don't mean electrical potential. What they mean is the electric pressure. So that's what they should call it. It's a direct pressure. It's not a potential, it's direct pressure. All right. Is the work done to move electric charge from one point to another within an electric field, typically measured in volts? So there's no electric field in the wire. There's just adding electrons and subtracting electrons, increasing the pressure between the electrons or decreasing the pressure between the electrons. Electricity plays a central role in many modern technologies, serving in electric power. Electricity plays a central role in many modern technologies. Well, I mean, it's like, why would you even have to say that sentence? Duh. I didn't know that. All right. Serving. I don't know what that even means. Serving in electric power, where electric current is used to energize equipment. It energizes it. Well, that's really exciting. Does it excite it? And in electronics, dealing with electrical circuits involved active components such as vacuum tubes. Why would they even bring up, the way archaic mechanisms? Transistors, diodes, and integrated circuits, and associated passive interconnected technologies. So isn't that funny? All right, so they didn't say anything about inductors and all the other crap you can have in a circuit, but whatever. Not even capacitors. They didn't say capacitors. I mean, one of the most useful. All right, a study of electrical phenomena dates back to antiquity. So again, sometimes the history is just so useless. With theoretical understanding progressively slowly until 17th, 18th century. So again, they're just going to keep telling us that Maxwell is everything when there's no theory behind Maxwell. Maxwell believed in an ether. Faraday believed in gears and pulleys. They didn't have any idea how the damn thing worked. All right. The development of a theory of electromagnetism in the 19th century marked significant progress, leading to electricity's industrial and residential applications by electrical engineers by century's end. Okay, so obviously by the end of the century, they really hadn't gotten all that far, frankly. But whatever. This rapid expansion of electrical technology at the time was driving force for the second industrial revolution. With electricity's versatility driving transformations in industry and society. So, I mean, obviously these things are all kind of parallel developments, but I mean, they figured out the combustion engine, and you could even go back to the steam engine, and all of these things, led to this industrialization. It's not just electricity. Electricity is integral to applications spanning transport, heating, lighting, communications, and computation, making the foundation of modern industrial society. So again, we could have done it some other way, but electricity is, you could argue for computers and such, you really need something moving the speed of light and all that kind of stuff. So it's really, it's huge in information processing, but it's not huge in trains, for example. A regular diesel, a diesel electric is a little more efficient than a regular diesel, but it's just that, a little more efficient. All right. Long before any knowledge of electricity existed, people were aware of shocks from electric fish. Ancient Egyptian texts dating to 2750 before Christ, and that's just an insane number, right? 3,000 years, 5,000 years ago, referred to these fish as the thunder of the Nile and described them as the protectors of all other fish. When, yeah, of course, they were shocking other fish. All right, electric fish were again reported millennia later by ancient Greek and Roman. Okay, so enough of this fish stories. All right, ancient. I mean, yeah, of course. Okay, obviously we have neurons that run on electricity. So obviously there has to be some rudimentary reason why electricity exists as a phenomenon, right? So maybe the first electrical thinking cell was actually for the purpose of, shocking food. Ancient cultures around the Mediterranean knew that certain objects, such as rods of amber, could be rubbed in cat's fur to attract. Okay, so we know this is just transfer of electrons. So you can do different things to take electrons off of one surface and put them on another surface. And it's the way you put them on another surface will decide how much pressure you can create. So something like a Van de Graaff machine you can sneak the electrons in from the bottom with no resistance, and they'll rise to the top, okay, because they have to go where there's the least pressure. So there's no pressure on the inside, so you sneak them in on the inside and they rise to the surface. So you can build up a huge number of extra electrons on the surface, okay, by sneaking them in the inside. All right. So those are all things you can understand. It just, again, has to do with pressure. All right, so we don't need to do amber stories and all that other crap. Okay, we can do a little bit of Benjamin Franklin, maybe. Electricity would remain little more than an intellectual curiosity for millennia until 1600s, when the English scientist William Gilbert wrote De Magnet, in which he made a careful study of electricity and magnets, distinguishing the lodestone effect from static electricity produced by rubbing amber. So obviously we know the static electricity stuff is more just about the fact that the higher pressure electrons do attract lower pressure. So yeah, that's going to happen. And then the magnetic effect just has to do with making those poles more obvious. All right. He coined the Neo-Latin word electricus, amber, blah, 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 rubbed, blah, 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 electricity, who cares? All right. Further work was conducted in the 17th and early 18th centuries by Otto somebody and Robert somebody and Stephen somebody and blah, blah, blah. Later by Benjamin Franklin conducted extensive research in electricity, selling his possessions to fund his work. So that's sort of an interesting statement. I never thought that Benjamin Franklin was short cash, but he did invest in so many projects that you could sort of understand him having moments where he was a little bit cash short. In June of 1752, he was reputed to have attached a metal key to the bottom of a dampened kite string and flown the kite in a storm-threatening sky. The succession of sparks jumped from the key to the back of his hand showed that lightning was indeed electrical in nature. I mean, you just have to kind of look at it to kind of know that, but okay. He also explained the apparent paradoxical behavior of a Leighton jar as the device is storing large amounts of electric charge in terms of electric consisting of both positive and negative charges. So, not really. It's just that you're using an insulator and you're storing the charge where it can't get away, can't go anywhere. So it's stuck on the individual atoms of the glass. And so you're just taking advantage of something that can store charge, but it can't move charge. All right, 1775, Williamson reported a series of experiments to the Royal Society on the shocks delivered by an electric eel. The same year, the surgeon and anatomist John Hunter described the structure of the fish's electric organs. So that was the whole Galvani thing. They figured out that this is a difference between chemical substances, so to zinc and copper, and going through all of that crap, so we probably don't need to do all that. While in the early 19th century it seemed rapid progress in electrical science, the late 19th century would see the greatest progress in electrical engineering through so it's all these people again. All right, so this isn't really it's not terribly useful anyway. In 1887, Hertz discovered that electrodes illuminated with ultraviolet light created electric sparks. So that's in 1887. So 20 years before Einstein figured out why it was doing that. Like more easily, in 1905, Albert Einstein published a paper that explained experimental data from the photoelectric effect as being the result of light energy being carried in discrete quantized packages, energizing electrons. So the idea is there's the charge force, the repulsion between the electrons, but and he's basically saying that the ability to move electrons is their momentum. There's a certain kernel of momentum. You know, you get 30 miles an hour, you get 60 miles an hour, you get 90 miles an hour. You don't do 45, you don't do these odd numbers. So that there's a discreteness, a discrete chunkness to how velocity is absorbed by electrons. I think that would be the best way to say it. This discovery led to quantum revolution. So the quantum part is the Planck part of recognizing that the force is in some sort of discrete little chunk, and that's all you're really moving is little chunks from one object to another. So if they would have stuck with momentum, then they could have understood it's just discrete chunks of momentum. The smallest thing, the smallest matter bit they can move is an electron. They discretely move electrons in chunks of momentum. So it goes 30 miles an hour, 60 miles an hour, 90 miles an hour. So you know it's in chunks. All right. Revolution. Einstein was awarded the Nobel Prize, blah, 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 for his discovery of the photoelectric effect. So we know the photoelectric effect is more complicated than just saying the photoelectric effect, right? The photoelectric effect has two phenomena. The first phenomenon is you hit any light on a metal, okay, or especially substances like, that you can dope to make them even better or more aggressive in this phenomenon. But you shine any light and you end up moving some of the electrons. They don't fly off the surface, but they move in the material, and that creates a current. So you move the pressure in a direction, all right, by shining light. Or you can shine high intensity or light, higher frequency light. That is, it hits more often in the same amount of time. It hits more often in the same amount of time. And you can actually give electrons enough momentum to leave the surface. And then you can give them even more by hitting with a gamma ray or an X-ray, and then you can make them leave the surface even faster. But it's all in chunks of velocity, chunks of momentum. All right, Einstein was we did that. The photoelectric effect is also employed in photocells, such as those can be found in solar panels. So again, you have two effects. You have the radiant effect of shining light and causing ionization that shoots electrons it reduces its voltage entirely by shooting electrons off the surface. Or you can have the more passive photoelectric, where you're just creating a current in the wire. The first solid-state device that was the cat whisker detector. So this is the crystal thing. So that's sort of interesting. All right, it's an obsolete electronic component used in some 20th century radio receivers that consisted of a piece of crystalline material which rectifies the alternating current radio signal. It was employed as a detector. All right, so that's how they made the first crystal radios. All right, was to take advantage of the fact that the crystal vibrated this way and created a current one way. All right. First used in the 1900s in radio receivers, the whisker-like wire is placed lightly in contact with the solid crystal to detect radio signals by contact junction effect. So I guess that's a spark effect in a sense. In a solid-state component with current, the current is confined to the solid elements and compounds engineered specifically to switch and amplify it. So they're just switching to a regular radio now, which uses a timing clock. Current flow can be understood in two forms: as negative charged electrons and the positively charged two forms: as negatively charged electrons and as positively charged electron deficiencies. So they're going to play the whole game called holes. So there's no holes. There's no holes in the sense that obviously an ion, a negative ion, is no hole. A positive ion means, yeah, you have a place where an electron can stick easily. So you have a very low pressure because you're missing an electron. So the electrons are really relaxed because there's not complete pressure. But that's what it's really about. It's more about just lowering the pressure. So there's never any positive hole. There's just lower electron pressure. All right, these charges and holes are understood in terms of quantum physics, so they're really not understood in any way whatsoever. They can't draw you a model of how it works. They can't simulate it. They can't do anything. So they just come up with all kinds of wooey, weird, bizarre-looking things and say, look, the woo monster swallows the hobgoblin. I mean, it's all just made-up crap. The building material is most often a crystalline semiconductor. All right, so no point in whatever. Solid-state electronics came into its own with the emergence of the transistor technology. The first working transistor, a gadolinium-based point contact transistor, was invented by John Burdeen and Walter Britton at Bell Labs in 1947. And so I sort of grew up in the age of the solid-state stuff really becoming functional, and all of that was trial and error, frankly. It wasn't theory. Okay, they made all this stuff work because they kept fiddling with it until it worked. All right, so electric charge, I guess we might as well do that. All right, the presence of electric charge gives rise to an electric force, electrostatic force. So again, the force is just the consequence of there's more electrons, it's going to repel electrons. If there's less electrons, it's not going to repel the electrons. So it's just about pressure. And charges force on one another. The effect was known though not understood in antiquity. You still don't understand it. You still can't draw a picture of it. So they have no explanation for why electrons attract and protons repel. So I've given you a simple diagram of why they can't do that. A lightweight ball suspended by a fine thread can be charged by touching it with the glass rod that has itself been charged with rubbing with a cloth. So you're just saying about I've either taken electrons off or I'm putting electrons on. That's all you're ever doing. Adding or subtracting electrons. If a similar ball is charged by the same glass rod, it is found to repel the first. The charge acts as a force to the two balls apart. Right, so the two balls have too many electrons on their surface. They look way too blue to each other, so they start acting just like they were electrons repelling. So once you cover the surface with electrons, you've essentially made a giant electron. And if you cover another surface with electrons, then the two electrons will repel. And obviously, if you don't have electrons covering one surface and it looks redder, then they'll attract. So you're just basically simulating the elemental function by giving the bigger objects the same appearance as the elemental players. All right, where the hell was I? Two balls that are charged with a rubber amber, who cares? However, if one ball is charged by a glass rod and the other by the amber rod, the two balls are found to attract each other. So you're just saying I have a lower pressure on one and a higher pressure on the other. Again, you can't simulate a true positive charge. You can just make it look, okay, less charge, more like a proton, but you'll never get it to a real proton. All right. These phenomena were investigated in the late 18th centuries by Charles Auguste de Coulomb, who deduced that charge manifests itself in two opposing forms. So, it's nice that you figure this two plus and minus thing, but I mean, it's north-south thing or electron-proton thing, but that's what it really should be called, is what it is. And all of the action happens by regulating the electron's pressure. You don't regulate the positive charge, you regulate the negative. So there's only one thing being manipulated. The discovery led to the well-known axiom, like charges, objects repel, and opposite charged objects attract. So again, that's the basic function shown by the big things charged, and that allowed people to see the little things underneath. So you're basically just doing the deduction work of saying, why is it doing it? There's got to be something in the interior system that allows that to happen. And the thing that gave it away was just saying, well, there must be two kinds of matter. if there's these two kinds of interactions, there must be two kinds of matter. Now, the thing they didn't figure out is that there's two kinds of force. The force acts on the charged particles themselves. Hence, charge is a tendency to spread itself as evenly as possible over a conducting surface. So we're just talking about a conducting surface. So again, a surface where the electrons are feeling each other's pressure. So every electron you add, all the other electrons feel the weight of it. Versus something like glass, where there's this rigid structure. Okay, you can almost say that almost round, the atoms are combined in some kind of configuration where they can't change their size. They can't accommodate any pressure change. They can't get bigger and they can't get smaller. They can't do any of that. So those electrons will not communicate any pressure. So you have to basically charge the whole ring of atoms, not just the single atoms. And they don't communicate their pressure. They have a rigid geometry that can't accept a pressure change. I guess that's the old way to say it. All right. The force acts on the charged particles themselves. Hence, charge has a tendency to spread itself as evenly as possible over a conducting surface. So over a conducting surface, the pressure is going to be on, the electrons are always going to end up being on the outside, the extra ones. But the pressure will spread into the conductor. And so the voltage, the pressure, will be throughout the entire conductor. All right. The magnitude of the electromagnetic force, whether attractive or repulsive, is given by Coulomb's law, which relates the force to the product of the charges and has an inverse square relation to the distance between them. So again, this is just the sort of obvious inverse square law that's the same for light bulbs, it's the same for gravity, it's the same for a lot of things. So anything where the force radiates from a central point and radiates in two dimensions. It radiates this way and then it spreads this way. So it starts with a certain density of force, a density of bits flying off of it, and so it's just like a radioactive isotope. Okay, there's a certain amount of stuff flying off of it, and as it spreads to a bigger and bigger area, the pieces get further and further apart by the inverse square law. So it's completely consistent with particle theory. The inverse square law is completely consistent with particle theory. So when they imply that the inverse square law has something to do with waves, no, it has a lot to do with particles. The electromagnetic force is very strong, second only to the strong interaction. So there's no strong interaction, right? This is the nonsense where they say protons can't get next to protons, where obviously if I put an electron between two protons, the two protons are going to get incredibly close to each other. Is also called the strong force. The strong nuclear force is a fundamental interaction that that confines quarks into protons. So that's just bullshit. Neutrons and other hardened particles, hadron particles. So it's just they're saying there's some kind of external force that's pushing electrons together, when no, the force that pushes them together is the elimination of the force between them. You're putting something between them so they can't see each other. It's that simple. You put something between two protons and now they can't see each other. They can get really close to each other. They can only repel each other if they can see each other. The strong interaction also binds neutrons, yeah, blah, blah, blah. So this is just all their fables. All right, but unlike the force, it operates over all distances. So they're talking about the strong force as if it stops somehow. There's the strong force is in some little area, and then it pushes the protons together, and then it doesn't do anything after that. It just hides. I mean, it's just a silly hobgoblin. They might as well just say hobgoblin every time they say strong force. They ought to just say hobgoblin force. It's just a complete nonsense. It's even more erroneous and non-real than bent space. It's just a nothing statement. A phantom force shows up, pushes things together, and then disappears. In comparison with the much weaker gravitational force, the electromagnetic force pushing two electrons apart is 10 to the 42 times that of the gravitational attraction pulling them together. And obviously that just has to do with the scale. Gravity is being produced by the movement of electrons and protons. So of course from their perspective, it's going to be a lot more intense because they're producing the force. You don't have any force without their function. They're the ones making gravity. So every time an electron is moved, it's changed a force from going the speed of light to a force going much less than the speed of light. And you can understand that deficit in the speed of the force is essentially a subtraction of energy. And that's what creates gravity. Somehow I hit the wrong button again. All right. Charge originates from certain types of subatomic particles. So there's only two types of particles. There's just electrons and protons. So again, they're never, I don't know when humankind will concede that there's only two kinds of matter in the universe, an electron and a proton. Everything is made of electrons and protons. There isn't anything else. You want to make a neutron, you just stick an electron and proton together. All the rest of that crap they talk about, neutrino, this, that, it's all bullshit. You're either pushing an electron or you have a force, but you can't have anything other. You're just moving an electron or you have a free force. That's it. None of this other crap exists. All right. Charge originates certain type of subatomic particles, the most familiar carriers, which are the electron and proton. So at least they're conceding, well, yeah, that does take up 99.9999% of reality. So why don't we just talk about electrons and protons, because everything else is nonsense. All right. Electric charge gives rise to and interacts with the electromagnetic force. So there's only one. The force is the force. It's the same force that creates light, gravity, magnetism, and whatever you want to call electricity. It's all the same force. It's force pushing electrons and protons. The force is what's between the electrons and protons, bouncing back and forth. The force is going the speed of light. The electrons and protons go something less than that unless they're hit by an intense amount of energy. A whole bunch of little force bits, like a gamma ray, very close together, a whole bunch of them, maybe 1 million of them. That's going to push something really fast. Okay. 1,030 miles an hour. You know, it's 30, 60, 90, 120. So if you build up a whole bunch of force behind an electron, you can get it going pretty fucking fast. All right. Anyway. Like one of the 4 fundamental forces of nature. Yeah, that's where it was. Experiment has shown, so this is where you really get into their lies, has shown charge to be a conserved quantity. Energy is a conserved quantity. You can't get rid of the little force bits. You can't get rid of the matter bits. All of it's conserved. So yes, no matter what you do, you can never kill the momentum. You can never kill the force or the matter. None of it disappears. All right. That is, the net charge within an electrically isolated system will always remain constant regardless of any changes taking place within that system. So again, it's not regardless of any changes. I mean, if I take a snapshot at any one time, something could be moved more that way. But obviously in a few seconds later, it's moving this way. Or a few milliseconds later, it's moving more that way again. So it just means that the net effect of all that movement is not going anywhere. But at any one moment, it is going here. And then another moment, it's going there. Another moment, it's going there. Just as you could take any one of my cells, and at any one moment, one of them's going down. But the fact is, at the same time, some of the other cells are going up, because gravity's pushing them back up. So, yeah, you can't just take the snapshot has to always recognize that it has to add up what every single bit is doing. Some fish in the school of fish can be swimming this way, and some are swimming that way, and some are swimming up, and then the school of fish doesn't go anywhere. So they're all balanced. Within this system, charge may be transferred between bodies, either by direct contact or by passing along a conducting material, which is a direct contact, obviously, such as a wire. The informal, so that we're just talking about, again, the pressure. So it's just electron pressure, and you're just saying, am I going to cause an electron somewhere else to move because I'm going to bring another electron into its view? I'm going to change the environment by pushing more blue into the environment, and the blue things are going to react to the fact that there's more blue in their environment. All right, the informal term is static electricity refers to the net presence or imbalance of charge on a body, usually caused when dissimilar materials are rubbed together, transferring charge from one another. Transferring electrons. You can't transfer anything other than the electrons. You can't transfer protons. You can only transfer electrons. So you're either increasing the pressure by adding electrons, or you're decreasing the pressure by subtracting electrons. They ought to get that really clear. The charge on an electron and proton is opposite in sign, so we all, duh. Hence, the amount of charge may be expressed as being either negative or positive. So it's just wrong to say so. The only thing there is added electron pressure or subtracted electron pressure. There's no zero electron pressure. There's just relative conditions. You can either have 50 pounds, 90 pounds, 500 pounds, but you can't have 0 pounds. Okay, and you can't have an infinite amount of pounds. Okay, by convention, the charge carried by electrons is deemed negative, okay, and the protons positive. So, and again, this is the wrong way to think about it, because all you're doing is changing the number of electrons. So there's no point in calling it the electron negative and the proton positive. All you're really talking about is the pressure is positive or negative. A custom that was originated with the work of Benjamin Franklin, right? So if he was going to make an assignment, he should have said electron is positive, because the electrons are what you're adding to create more pressure. So more pressure is what you're really pushing through the wire and all that kind of stuff. It's usually the way things are going to work. And voltage and amperage move in the same direction. So this made a total mess out of Maxwell's equations, and now we have this idiotic notion that somehow the number of electrons moves one way and the pressure of the electrons move the other way, which doesn't happen. The amount of charge is usually given by the symbol Q and expressed in coulombs. Each electron carries the same charge of approximately blah 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 blah. So yes, each electron is a certain size. They're all the same size. They carry the same amount of capacity to reflect the universe. They all look exactly the same. So they all add the same mass to whatever surface they're added to. All right, the proton has a charge that is equal and opposite, so in this it's irrelevant because it's stuck in the nucleus. Charge is possessed not just by matter but also by antimatter, so what the fuck, right? Just absolute nonsense. Each antiparticle bearing an equal and opposite charge to the corresponding particle. So look at what they show for antimatter, right? The same 1956 photograph of this line that somehow proves this is a positron. Somehow it went in a proton and it came out a positron. Says them, right? Well, or else it's a positron through the whole path. This is a little strip of lead, by the way. What the fuck? Says them. All right. Charge can be measured by a number of means. An early instrument was the gold leaf electroscope, which, although still in use for classroom demonstrations, has been superseded by electronic electrometer, which I haven't seen. So I have to go get one of those electronic electrometers. Yeah. So that doesn't look like a huge advance there. That sort of looks like the same thing. But they have an electronic version, whatever that would be. All right. So yeah, we'll probably call that a video. All right. And then we can get into current, and let's see what else we have. Yeah, then we can talk about the nonsense of the field, because the field is really a magnetic field. It's not an electric field. It's an appearance field. All you can do is change the appearance of something to the rest of the environment, and the appearance is getting changed when you add or subtract electrons. It's that simple. If you add electrons, it gets more blue. You add less electrons, it gets more red. Not that complicated. And if you polarize that is, it's more red up here and more blue down here, other polarized objects can see that change and they'll turn to meet your dipole. You create a dipole, the other dipoles will turn so that it's proton against electron and proton against electron, so they can attract, so they'll turn. All right. So enough of a video and such, but I think I made it. I think I said enough to indicate there is a mechanical theory. You can understand it mechanically. It's not as abstract and complicated as they make it sound. It's just pressure. And you could create an illustration of it with grains of sand in a tube, and you push more sand in, and the faster you push the sand in, the bit of sand, all that momentum has to move through the sand, that kind of thing. All right, anyway, till the next time, and such and so forth and whatnot.